back to HackCode. In this video, we will be unraveling the LeetCode problem, Maximum Product Subarray. This challenge requires us to find the subarray within an array which has the largest product. It's a fascinating problem which tests our ability to understand array manipulation and introduces us to the concept of dynamic programming for optimal solutions. So we're going to explore both brute force and optimized solution. Let's get started. So the problem statement is, given an integer array nums, find a subarray that has the largest product and return the product. The test cases are generated so that the answer will fit in 32-bit integer. So first example is this one. Output is 6. Why output is 6? Because this is the largest product. So we got 6. That's how we got 6. 2 to 3. So here in example 2, the output is 0 because the result can be 2 because 2 comma minus 1 is not a subarray and it's a subset but not a subarray. That's the main catch. So the output is 0 for this. So constraints here, remember we have nums is in the inclusive range of 1 and 2 into 10 power 4. 2 is a key. If they haven't had given this 2, we would have done it in n square because 10 power 8 operation can be done per second in a per given processor. So here the norms of I, that means element in an array ranges from -10 to +10. So the product of any prefix or suffix of nums is guaranteed to be a 15 in 32-bit integer. So let's look into the brute force approach first. So brute force. The brute force method for this problem involves in checking the product of every possible subarray and then returning the maximum found product found. So this approach is straightforward but not efficient for the large arrays due to its high complexity. First of all, let's look into what subarray. That's how we're getting more area. So a subarray is a contiguous part of an array, unlike subsets, which consists of a non-adjacent elements from an array. A subset must maintain the order of the elements as they appear in the original array, and it must be made up of an element that are adjacent to each other. As we see here, these are the subarrays of the ABCD. So this can form from A, and A itself be a subarray, and AB, ABC, ABCD. Similarly, this follows. So example, if you have an array of 1, 2, 3, 4, then 2, 3 is a subarray. 2, 4 is not because it skips over 3. It's a subset. It's not a subarray. So yeah, hope you got an idea of what's subarray. So let's go into brute force approach first. So here, as we discussed, we go over all possible subarrays and find the maximum product and return the maximum product. It's very straightforward. So here for J, see, remember we keeping J is an inclusive range of I because A, as we seen here, A can be subset of ABCD. So that's how we want to have this element to be inclusive. So keeping it part of this. So here we are accumulating product or as we iterate over J, so nums of J. So that's how we get the product accumulated. So accumulated product is equals to accumulated product into nums of J. It was initialized to 1 before. So maximum product is max of max product and accumulated product. Initially we give it to 0, nums of 0 as a maximum product. So and at the end we return the maximum product. So here the time complexity is n square, where n is length of nums. Space complexity is O of 1. So let's go to the other approach, that's dynamic programming. The brute force method is simple but it's not efficient. So here's how dynamic programming helps optimize the solution to be an O of n. So an high overview, we iterate through the array while tracking the maximum and minimum product of subarrays that at the current element. So basically we should be keeping track of two things, maximum and minimum product of subarrays that end at the current element. And then this accounts for the fact that a negative number can flip the maximum and minimum values. So by keeping track of both maximum and minimum products to the current point and updating the global maximum, we ensure that we can handle arrays containing negative numbers efficiently. We have seen that input range is from the elements range is from -10 to +10, right? So that's how we got to know that we should handle negative elements or negative numbers. So let's look into the code. Here the key components are global max and previous min. So global max keep track of the maximum product of any subarray encoded so far. So what is this previous max and previous min for? This store the maximum and minimum product of subarrays ending at the previous element and respectively. So logic flow. So we start with, I'm just telling a overall idea and I'll walk through the code. So we start with initialization of the global max, previous min and previous max to the nums of 0. So here since we already initialized to 0th element as a this global maxer, we start iterating from 1. So here we keep track of two things here: current max, current min, and we apply it to the global max based on what is the current max. So what is current max here? The current max is there's a maximum product ending at the current element. It's a maximum of the three values: the product of the current element and the previous max, and the product of the current element and the previous min, and the current element itself. This is how current element can be maximum, because the product of the previous thing can be less than 0 or equal to 0, and here there could be cases where current element greater than 0. So this considers the possibility of negative numbers turning into the positive when multiplied by negative current element, and when the current element is greater than 0, being the previous elements or less than 0 whose products is. So what is current min for? It is similar to current max, but for finding the minimum product. It considers case where a negative current element can turn into a positive previous max and into a negative product. So which might become the maximum product if another negative number is encountered later. And then we keep on updating the global maximum. So after calculating the current min and current max, the global max is updated if the current max is larger than the current global max. So and then we prepare for the next iteration. So previous max and previous min are updated with the current max and current min to be used for the next iteration. So that's how, like, again we'll just do a walkthrough of code here now. So here, as we already know, you should be aware that we are iterating from nums of 1, because we already initialized the global max nums of 0, right? This is the basic subarray nums of 0 would be. So we already passed that one, and then we are iterating from nums of 1, and here we're keeping the current max, which is the maximum of these three things. Previous max into num is a conventional case where the previous max is greater than 0 and num greater than 0. Previous min into num is a case where the previous min is less than 0 and num less than 0. And the num is a conventional case where the previous product less than 0, less than or equal to 0, and num is greater than 0. So keeping this in view, we update the global max from, and then we just prepare for the next iteration, and then we return the global max. Hope it clears the point here. So here the time complexity is O of n, where n is the length of nums, and space complexity is O of 1. So first let's break down how dynamic programming is applied in this solution, right? So here we're doing the sub-problem optimization, right? At each step of the iteration to the array nums, the solution maintains the maximum and minimum product of subarrays ending at the current index. This allows the algorithm to consider optimal subarray solutions up to each element. And next is optimal substructure. The maximum product subarray ending at the current index can be derived from the maximum and the minimum product subarrays ending at the previous index, along with the current element. So this ensures the algorithm considers the impact of each element and overall maximum product. And next step is memoization. So instead of recalculating the maximum and minimum products for all subarrays at each step, the algorithm only updates the maximum and minimum product for the current index based on the previous index. So this memoization strategy avoids redundant computations and improves efficiency. So overall, the solution effectively applies dynamic programming principles to efficiently find the maximum product subarray, so demonstrating a clear understanding of TP optimization techniques. So let's go over the demo. So We try submitting the brute force approach. Definitely you do TLE. Only 187 out of only 3 cases missed though. So we try submitting the DB solution. So yeah, so it beats 93.8% of the Python solutions. It's the most efficient solution we got so far. So yeah, so the conclusion is like in this exploration we've seen how a brute force approach can be a straightforward way to tackle the max product subarray problem, but it's not efficient for the large data sets. That's why the last 3 test cases failed. So by employing the dynamic programming, we significantly improved our algorithms efficiently, showcasing the power of optimizing our solutions. So whether you're just starting your coding journey or looking to brush up your dynamic programming concepts, this problem provides a great learning opportunity for same. Thanks for tuning into this episode of Hackwork. If you found this video helpful, be sure to give it a thumbs up and subscribe to the channel for more coding tutorials and comments on tips. If you have any questions or suggestions, please drop it